Okay, this is review lecture 25b, I think it is, on the eye. The human eye is roughly spherical, about 2.4 centimeters in diameter. That's about an inch. The transparent cornea and lens are the eye's refractive elements. They act like the compound lens of a camera. The cornea does most of the refracting. The lens does the final focusing called accommodations. The iris is like the iris in a camera. It will expand or contract to control the amount of light. In other words, it expands and contracts the pupil. The retina is the detector. It generates electrical impulses that are transmitted to the brain by the optic nerve. The eye is also filled with a clear gel-like fluid. This is called the aqueous humor. That's the one that's behind the cornea, or the vitreous humor, which is behind the lens. The indices of refraction of the aqueous and vitreous humor is about 1.34, only about slightly different from water. The lens has an average index of 1.44. The pupil is a variable diameter aperture in the iris, and it automatically opens and closes to control the light intensity. The aperture can vary from about 1.5 millimeters in very bright light to about 8 millimeters in darkness. The f number of the eye varies from roughly f3 to f16, very similar to a camera. Now, the eye's detector is a retina. It contains light-sensitive cells called cones. Those are the color or day vision, and rods, which are the black and white and night vision. The figure shows the wavelength responses of the cones and rods. And of course, as I say, there are three types of cones. Notice the rods are very sensitive to blue light. Okay, and this is your night vision. The cones are your day vision. They are sensitive to three different colors. The relative response of the different colors in the cones is interpreted by your brain as light of a particular color. Other animals with slightly different retinal cells can see ultraviolet or infrared, the wavelengths that we normally cannot see. Cats and bees can see in UV. Pit vipers, such as rattlesnakes, can sense IR, or infrared. Now, most of the refracting of light is done by the highly curved cornea. The fine adjustments to focus is done by the ciliary muscles, which change the curvature of the lens, changing its focal length. Tensing the ciliary muscles causes accommodation, which decreases the lens radius of curvature and thus decreases its focal length, giving us our near vision. Our far vision occurs when the ciliary muscles relax, letting the lens assume a less curved shape, increasing its focal length. Ciliary muscles are here on the sides here. The furthest distance at which a relaxed eye can focus is called the eye's far point. The far point of a normal eye is at infinity. That is, the eye can focus on objects extremely far away. And in this case, the ciliary muscles are relaxed for distant vision. The closest distance at which the eye can focus clearly using the maximum accommodation is the eye's near point, otherwise known as NP. And the normal eye has an NP of about 25 centimeters, but this varies with individuals and with age. It typically increases with age. Now, corrective lenses are prescribed not by their focal length, but by their power. The power of the lens is the inverse of its focal length. So the lens power, also known as the diopter, is P equals 1 over F. The SI unit of the lens power is the diopter. It's abbreviated D, and 1D is 1 inverse meter. Thus, with a lens of a focal length of positive 50 centimeters, has 0.5 meters, has a power of 1 over 0.5 meters, or plus 2.0 diopters. This would be a convex or positive lens prescribed for farsightedness. An optometrist prescription might read minus 2.25 / minus 2.50 in diopters. And of course, this is implied for the right-left eye. So right-left eye. This would mean that the focal length is minus 0.44 meters for the right eye and minus 0.400 meters for the left eye. Now, eyes can be mismatched and require different corrections. A person who is farsighted can see faraway objects, but even then must use some accommodation rather than a relaxed eye. But his near point is larger than 25 centimeters, often much larger, so he cannot focus on nearby objects. This is called hyperopia. The cause of farsightedness is an eyeball that is too short for the refractive power of the cornea or lens. In other words, the eye's lens is too weak for the length of the eyeball and needs some strengthening assistance from a positive corrective lens. So what happens is, instead of focusing on the retina, which is where you want the light to focus, it focuses beyond the eyeball, somewhere in the back, in your head. With this condition, the eye needs assistance to focus the rays from the near object to a closer than normal retina. This assistance is obtained by adding the refractive power with a positive, that is a converging lens. This lens forms an image that is the object for the eye's lens. You want the person to be able to focus when the object is 25 centimeters, that is a distance of 25 centimeters. A corrective lens should form an upright virtual image at the person's actual near point which should be out here. And when this happens, hopefully the focused image comes right to the retina and therefore can be seen without being fuzzy. You want the person to be able to focus when the object is 25 centimeters, that p equals 25 centimeters. The corrective lens should form an upright virtual image at the person's actual near point, that is I equals NP. So 1 over P plus 1 over I equals 1 over F, or 1 over 0.25 meters minus 1 over NP equals D. A positive lens is needed. So this is an example. We're going to correct this condition. The near point of a left eye of a person with hyperopia is 150 centimeters. What prescription lens will restore normal vision? Ignore the space between the lens and the eye. And you should be doing this before you view the videos or come to class. Okay, the physics of this is thin lenses. Because the person can see objects 150 centimeters using maximum accommodation, we want a lens that creates a virtual image at a position I equals minus 150 centimeters. It's negative because it's a virtual image of an object held at P equals 25 centimeters, which is the desired near point. The knowns and unknowns, P is minus 1.50 meters and I equals 0.25 meters. Now notice you want to convert these to meters because the diopter is in inverse meters. So the formula is diopter equals 1 over P plus 1 over I, or 1 over 0.25 meters plus 1 over minus 1.50 meters. That is 3.3 diopters, or the power of the lens. So this is a positive or converging lens and is used to correct hyperopia and also the age-related farsightedness called presbyopia. Now, presbyopia, the nearest normal near point is considered to be 25 centimeters for young adults. Unfortunately, the near point increases with age as the lens loses flexibility and the ciliary muscles weaken. This causes a refractive error called presbyopia, which is literally old age vision. It's a form of farsightedness and causes its victims to typically hold their books at arm's length and squint when trying to read or do close work. Reading glasses, which employ convex or positive lenses, are used to bring the near point to a more comfortable distance for reading and close work. So it's basically you're correcting a farsighted eye. So in other words, this is where the lens would focus, the eye would focus without the glasses. So in other words, focus is here instead of here. When you put the proper lenses in here, proper glasses, a positive lens of the proper strength, then the focal point will come right to the retina. Now, myopia is a person who is nearsighted. This person can clearly see nearby objects when their eyes relax and extremely close objects by using accommodation, but no amount of relaxation allows her to see distant objects. This is caused by an eyeball that is too long for the lens. So rays from a distant object come to focus in front of the retina and have begun to diverge by the time they reach the retina. So in other words, they come to focus here instead of here where we want them. So the eye's lens is too strong for the length of the eyeball. Because the eye's lens is too strong, we need a diverging lens to slightly defocus the rays and move the image point back to the retina. So we need a corrective lens that forms a virtual image at her far point, so I equals FP, when the object distance is at P equals infinity. That virtual image acts as an object for the eye when fully relaxed, can focus the image onto the retina. So the far point of a left eye of a person with myopia is 200 centimeters. What prescription lens will restore normal vision? Ignore the space between the corrective lens and the eye. The physics of this is thin lenses, corrective lenses. For objects at infinity, P equals infinity, we want the lens to create a virtual upright image at the person's near point, so I equals minus 2.00 meters. Now notice we converted to meters. Because the person can clearly see for objects at that distance. It is a virtual image, so I will be negative and a diverging lens. So we know we want to convert everything to meters because diopters is an inverse meter, so I equals minus 2.00 meters and P equals infinity. The formula is diopter equals 1 over P plus 1 over I. And of course, P is at infinity. This will turn into 0. So it just becomes 1 over minus 2 or negative 0.5 diopters. This would be the prescription power of the lens. So myopia is corrected with a diverging lens. If the near point of your eye is at 75 centimeters, you are farsighted. In other words, it's greater than 25 centimeters. If your vision is improved with lenses that look like this, you have myopia. You're nearsighted. Thank you.